work done at the moving boundary of a simple compressible system. We have already noted that there are a variety of ways in which work can be done on or by a system. This includes work done by a rotating shaft, electrical work, and the work done by the movement of the system boundary, such as the work done in a moving piston in cylinder. In this section, we will consider in some detail the work done at the moving boundary of a simple compressible system during a quasi-equilibrium process. Consider a system, the gas contained in cylinder and piston as this picture. Remove one of the small weight from the piston. This is position 1, state 1 and state 2. So A, remove one of the small weight from the piston. Which will be cause the piston to move upward at distance dl, cause the piston to move upward a distance L, upward a distance dl. We can consider this quasi-equilibrium process and calculate. So we can assume the quasi-equilibrium process and calculate the amount of work done by the system during the first process. The total force on the piston is equals to PA. A is the area and P is pressure. Therefore, the work PA multiplied to the distance, which is dl, or we can write is dB, delta W is dV. The work done at the moving boundary during a given quasi-equilibrium process can be found by integration of this relation However, this integration can be performed only if we know the relation between P and V during this process. The relationship may be expressed as an equation. So we should have a relation between P and V. So we have, maybe we had a graphical as an equation, or shown as graphical relation. Let us consider a graphical solution first. Graphical solution. We use an example compression process such as occurs during the compression of air in the piston and in a cylinder shown in this picture. At the beginning of the process, the piston is at position 1. This position 1, as shown also in the diagram of PV, and the pressure is relatively low. The state pressure is relatively low. This state is represented on a pressure volume diagram in the PV in this point. At the conclusion of the process, the piston is in position 2, this point. And the corresponding state of the gas is shown at point 2 on the PV diagram. Let us, in this case, the higher pressure state. Let us assume that this compression was a quasi-equilibrium process and that during the process the system passed through the states shown by the line connecting state 1 and 2 on the PV diagram. The assumption of a quasi-equilibrium process is essential here because each point on line 1 and 2 represents a definite state, and these states correspond to the actual state of the system only if the deviation from equilibrium is infinitesimal. Definition of deviation. From equilibrium is infinitesimal The work done on the egg during this compression process can be found by integration of the dV. So the work from point state 1 to state 2 is the symbol W from 1 to 2 is to interpret it as the work done during the process from state 1 to state 2. It is clear from the PV diagram that the work done during this process is this expression. In representing by the area under curve 1, 2, the area of A1 to BA shown in the blue color. In this example, the volume decreased and area represented work done on the system. If the process had proceeded from 2 state to 1 state along the same path, the same area would represent work done by the system also. Further consideration of PV diagrams shows in the picture here. Leads another important conclusion. It is possible to go from state 1 to state 2 along many different quasi-equilibrium paths such as A, B or C in this picture. So we have a note, it is possible go from state 1 to state 2 along different paths such as A, B or C. Since the area under each curve represents the work for each process, the amount of work done during each process not only is a function of the end state of the process but also depends on the path. So from this relation expression we can conclude to the work not only depends on the state 1 and 2 but also depends on the path the path following. In going from one state to another. For this region, work is called a path function. So the work is a path function. In mechanical parlance, in mathematical parlance, we have inexact differential. For example, delta over path functions in inexact in mathematical. This concept leads to a brief consideration of point and path function, or to use other terms, exact and inexact differential. Thermodynamics properties are point functions. are point functions, a name that comes from the fact that for a given point on a diagram, the state is fixed. Is for a given on a diagram or surface, thermodynamic surfaces, the state is fixed. And thus there is a definite value for each properties corresponding to this point. The differentials of point function are exact differential, So we have the dB b second minus b1 for the point functions. Thus we can speak of the volume in state 2 and the volume in state 1, and the change in the volume depends only on the initial and final state. Depend on initial and final state. Work, however, is a path function, we said before. For, as has been identified, the work done in a quasi-equilibrium process between two given states depends on the path followed. The differential of path function are inexact differential, and the symbol for differential is delta. We'll be using this book to designate inexact differential. Differential of path function. Thus for work we write the differential of inexact parameters in this book, right as this expression. It would be more precise to use the notation WA2. For example, we can, for a process from 1 to 2 from A, the path we can write, for example, 2A or 2B. This is distinguished between the paths. However, the notation 1 and 2 indicated that the process between state 1 and 2 have been specified. Note that we never speak about the work in the system in state 1 or state 2. We never write W2 or minus W1 because we never speak about the work. At point 1 state or state 2, so we never write W2 minus W1. We talk about the process from the process 1 to a process down from one state to two states. In evaluating the integrals, we should always keep in mind that we wish to determine the area under the PV diagram. In connection with this point, we identify the following two classes of problems in this classification of work. The relationship between two types of problems. Between P and V is given. In terms of experimental or in graphical forms. Therefore, we may evaluate the integrals by graphical or numerical integration. The relation between P and V makes it possible P and V make it possible to fit an analytical relation is now as a function is now and an analytical relationship direct integration possible. Is possible. So these two type of problem, for example, of the one common example of the relation between P and V is a process called a polytropic process, on which PVN equals to constant for a polytropic process. So we have we should obtain a relation between P and V. We know PVN equals constant, so P1 V1 and also P second V second also are constant for this system. From this we can write P equals to constant on Vn. In this case, to integration, with replacing constant at first P1 V1N and at second P2 V2N. At first we have equals to constant on V second V1 substituting constant this as this relation minus P1 V1N V1 is N Now we can write the final expression P second for N. If N equals to 1, we should write from the first integration PV const P1 B1 P second V second. dV on V const L and V second on V1. We have two equation P1 P second V second Note that in these two equations, we did not say that the work is equals to the expressions given in these equations. These expressions give us the value of a certain integral. That is a mathematical result. Whether or not the integral equals the work in particular process depends on the result of thermodynamic analysis of that process. It is important to keep the mathematical result separate from the thermodynamic analysis, for there are many situations in which work is not given. For example, in the basic form of integral, the polytropic process as described demonstrates one special functional relation between P and B during a process. There are many other possible relations, some of which will be examined in the problems at the end of the chapter. The next section in this chapter is about the other systems that involve works.